The Cline repository houses a layered, production-grade TypeScript SDK monorepo, a system designed to operate independently of any specific interface or IDE. The architecture features 4 distinct packages: shared contracts at the base, an LLM gateway for 50+ providers, a stateless agent loop, and a stateful orchestration core. Dependencies point downward. Developers interact with the system through a singular composition route, the ClineCore Facade. Managing an agent with this degree of autonomy requires an architecture built around transport boundaries, unbounded iterative loops, and state reversion hooks. By analyzing Cline as a state-managed harness rather than a simple extension, we can see the primitives required to architect autonomous tooling for scale. We begin by tracing the data flow of a single turn. A user message originates from a host application and reaches the ClineCore Facade. ClineCore holds no conversation state. Instead, it immediately delegates the user turn to a selected runtime host. This logic depends on a runtime host boundary, a primitive that allows the SDK to target 3 distinct execution environments without modifying the underlying agent code. The local pathway runs fully in process. The hub model operates against a detached daemon, allowing multiple external clients to attach to and resume long-lived sessions from a single shared state. The remote execution path isolates the operation entirely, pointing the SDK toward an explicit external server. Within this architecture, host applications, whether a CLI, a VS Code extension, or a web hub, function as thin, interchangeable clients. They do not house the agent logic. This strict transport-neutral boundary is the foundational requirement for allowing stateful agents to operate independently of a specific IDE. Once the turn is delegated, the stateful orchestrator provisions a fresh, entirely stateless agent runtime object for the duration of that turn. The runtime executes a 4-step iterative loop. It streams the model, parses tool calls, executes those calls, and pushes the results back as messages to seed the next iteration. The max iterations parameter is strictly optional and carries no hard-coded default value. If the caller omits it, the variable remains undefined. This configuration creates an unbounded loop. The agent will continue to iterate until an external condition or the model itself triggers a stop. 3 conditions terminate the loop. The model returns a turn with no tool calls, an external abort signal is received, or the model executes a completion tool, such as submit and exit. The architecture contains no inner retry subloop. API and authentication retries are handled by a host-level wrapper, leaving the core agent loop purely iterative. Behavioral safeguards, including repeat call detectors and consecutive mistake counters, sit in the orchestration layer outside the loop to terminate runaway processes. By stripping the loop of internal state and safety bounds, the harness forces execution control into the orchestration layer, keeping the runtime logic simple and transportable. Tool Dispatch handles 9 built-in defaults, dynamically wrapped MCP endpoints, and 18 specialized team tools for multi-agent coordination. To prevent conflicting file modifications, the harness enforces mutual exclusivity between the apply patch and editor tools, allowing only one edit primitive per session. Every executed tool returns a standardized payload to the harness. It contains exactly 2 fields, a string for the output and a Boolean flag for is_error. This object omits the LLM content field. Returning bare outputs ensures that the host application owns all LLM-facing prompt formatting. This creates a clean architectural waste between the execution logic and the presentation layer. Procedures follow a similar logic. Skills are invoked dynamically via tool calls. A dynamic description advertises available skills to the model, which allows the base prompt to remain small. In contrast, rules bypass tool dispatch. They are read from flat files and injected wholesale into the system prompt at the start of the session. Minimizing the tool contract to raw outputs isolates the core loop from the specific formatting requirements of over 50 different model providers. The authorization gate relies on a coarse, single Boolean tool policy per tool. If no callback is configured, the gate fails closed. However, a denied request simply returns an error payload, allowing the loop to continue iterating. The production harness operates without any OS-level isolation or sandbox to protect the host system. When the model calls run commands, it triggers a bare host spawn. The process inherits the complete environment of the parent process. Security is managed not through containment, but through the shadow Git checkpoint network. Before any file edit, a hook creates a private Git stash. If a model makes a destructive change, the harness can recall the previous state. This restoration sequence, reset, clean, and stash, instantly undoes incorrect model behavior. In local development environments, protecting the system relies on making all destructive actions instantly and completely reversible. An unbounded tool call loop eventually risks exhausting the context window. The harness must intervene before the next model stream is initiated. While the canonical transcript is permanently preserved in the repository, the model receives a dynamically projected, budgeted sidecar. When the filled context window reaches 90, telemetry signals for task completion rely entirely on model self-attestation, the model itself deciding when to call the submit and exit tool. Correctness is measured post hoc. The framework uses external capability evals to check file contents after the agent finishes, rather than enforcing constraints during the run. A production architecture of this type is defined by its transport boundary, its unbounded loop, and its checkpoint-based safety net. Scaling an autonomous harness requires a fundamental shift, moving away from rigid perimeters and internal testing loops in favor of coarse orchestration, explicit trust boundaries, and instant reversion.